Hi, in this video I'm going to talk about the application of differentiation in optimization problem. Okay, optimization problems. Okay, let's look at the problems from the given question in the lecture notes. So where that a rectangular is made up of a piece of cardboard, right? It's a made up of a piece of cardboard. And this cardboard is made up of 24 cm long, right? You have 24 cm long, all right, and 9 cm wide, 9 cm wide and long, right? So by cutting out identical square from the four corner, so identical square, identical means that all the four square is cutting out. This is how you're making a box, right? Yes or not? So you're cutting out the identical square, which is all of the same size from the corners, from the four corners. So, and this identical square from and turning up the side. Okay, so then the question is, after you cutting out this, you're cutting out. So you're cutting out. This is a cardboard. Okay, a rectangular cardboard. So you want to build a box, right? A box for a present or anything. So then you cut out a same square, right? So you cut out, or I can say I don't know how and they never tell me I cut for how long is this, like the side. So I just put this to be x, right? Just put this to be x, which unknown, I don't know how long should I cut, but I know it's a square. That's why I put xx is a square. So as I cutting out, so this will be left here to be empty, right? Here to be empty. So later I cut out, I cut out this, and I have an empty square here, right? And here also will be having a empty square. So where all of these have an empty square here, so it will become something like this, the shape, the shape of the cardboard. So now, then they turn up the side, So the question is saying that turning up the side, okay, turning up the side. So you go and fold it, you fold the side, and you're turning up the side. As you're turning up the side, you are forming a cuboid, right? You are forming a cuboid. So as I draw, you can see. So I will form a cuboid. So where there are two rectangular here. So when I'm turning up this thing, this will become your height, right? As you're turning up, so this will become your height, So x. So if I joining this, right? Then this will be your cuboid, right? So means that the side that you're cutting out, this will become your height for the cuboid, right? X and x. So how about the length here, right? The length here is no longer 9 cm. It's not 9 cm, right? Initially, all this is 9 cm. 9 cm, but I have cut out x and x from here. So now I can say that the remaining part here, will be 9 minus x. So become 9 minus with 2x. Very important. So it's not 9, it's 9 minus x, right? Because you're already cutting out x here. And this one, the long, right? The length here is actually 24, right? It's 24. But after you're cutting out the x, right? X and the x here, so you are getting, means the length here, alright? The length for the base here, this length here will become, this will become the base, right? The base of the cuboid, So you are getting 24 minus with 2x, right? Minus with 2x. So now you have all the dimension in terms of x. So the height, the length, and the width, and the width, right? So then you okay, later that that they want to find the dimension. Okay, find the dimension means the height, the length, the width, all right? So that the box of maximum volume, and means that the box will become maximized. Okay, maximized. So this is a problem of optimization problem. So optimization problems is relate to maximum and minimum, alright? Either it's maximum or minimum. So optimum value. So it's like relative extremum, alright? Relative extremum. So for this case here, we have to form a function because they want to find maximum volume, right? So by calculus, you have to get a function for volume for these cases. The volume will be always the length, the width, 9 minus 2x multiply with 24 minus 2x and multiply with x, right? So the width times the length times the height, you will get the volume of the cuboid. And in terms of x, right? Because this is a function that I don't know how much, how big should I cut or how small should I cut? What size is suitable so that it will become maximum, right? Means the volume. Let's say you put water, of course you want maximum volume, right? So now you are going to expand this so that it become a function, all right? So, okay, let's see. So I'm going to expand this into here first. 9x minus 2x to the power of 2. 24 minus 2x. So 9 multiply 24. Okay, just expand the bracket. Just expanding. So 9 multiply 24, you have 216. 216x, right? 216x followed by 18x to the power of 2, right? Negative 2 times 9, negative 18, x to the power of 2. Okay, minus with 2 times with 24. So 48x to the power of 2, right? Negative 48 to the power x to the power of 2. And lastly, negative positive 2 to 4x to the power of 3. 4x to the power of 3. So if you rearrange this, this is actually a polynomial function, right? It's a function, it's a cubic function. So 4x cubed minus 18 minus 48. So you have 66x to the power of 2 plus with 216x. Now you see, you are getting a cubic function, which the volume can represent is a cubic function. So as you remember that calculus, okay, from differentiation, right? So if you want to find the maximum, the extremum value, or we said this is optimum value, so we are going to differentiate this and equate it to 0, right? So the first thing here will be, you want to find optimum, either maximum or minimum value, you have to find the stationary point, all right? The stationary point. So it means that the stationary point here is dvdx. So you have to differentiate first. So 3, 4, 12x to the power of 2, right? 3, 4, 12x to the power of 2 minus with 2 times 66. So you have 132x plus with 216. So of course, if you want to find for optimum value, you have to differentiate, right? And you have to find the stationary point so that you know where's the maximum and minimum point. So now you take dvdx equate to 0. dvdx equate to 0. So it means that 12x to the power of 2 minus 132x plus 216 equals to 0. Right? So let's look at how to factorize this. Okay, let's divide everything by 12. So you have x squared minus with 132 over with 12. You have 11x plus with 216 divided by 12. You have 18 equals to 0. Right? So now you factorize and getting the stationary point. Right? Or we find a critical number here. So xx 18, okay, 2, 9, 18, right? And you have negative, right? Negative 2, negative 9, you have negative 11. So you're getting two value. You get two value of x. But this two value of x is the stationary point, right? But is it okay if you choose 9 or choose 2? So logically, you won't choose 9, right? Try to pause the video and think why you don't choose 9. Because you know that everything here is 9, right? Maximum is 9, right? The length for the box is 9. If you're cutting out the square with x to be 9, then the whole then you will be no box. You can't form a box also, right? You can't form a box. So where if you're cutting out 9 and 9, you can't form a box, right? It's not true, okay? This one, but it's a solution, but it's not fit for this problem here. So x equals to 2, okay, means that if you're cutting out 2, it seems logic. You're cutting out 2 and 2, and you're cutting out 2 and 2, then you can form a, because this is 9, right? Then you get 7 here, then you get 24 here, right? Yes or not? So you can't cut a square if you use 9, right? You will cut the whole thing here, right? You won't cut, you get 9 and 9. You can't cut a square, right? So you can't form a box. So for x equals to 2 is the one that we need to check whether it's maximum or minimum, right? So as you know that there is a second derivative test, right? Second derivative test. So the second derivative test to verify, yeah, usually this will be the only solution, then it will be true, but we have to verify. Second derivative test. Second derivative test. So we differentiate the dvdx for one more time. So we have 24x. Alright, 24x. 24x minus with 132, right? Minus with 132. We test the value, alright? So when x is 2, right? When x is 2, so you're putting 2 inside here. So d2v dx2 when x is 2, right? So it's equals to 24 times 2 minus 132. You see that this will be a negative number because 48 minus 132. A smaller number minus a bigger number, of course it will getting a negative number, right? So if you still remember, if your second derivative test, you get a negative value, right? Means that this is a maximum point, right? It's a maximum relative maximum point, right? So means that in this case you have already shown that it's less than 0, right? If more than greater than 0, it will be a minimum, relative minimum. So because you want a maximum volume, so the test actually already tell you this is a suitable value. So means that x equals to 2 is the relative maximum point. Alright, then they said that the dimension of the box of maximum value, of course the dimension here will be, right, all the length. So means that 9 minus 2 times with 2, right? 2 multiply with 24 multiply minus with 2 times 2 multiply with 2. So 9 minus 4, you have 5, right? So here you have 24 minus 4, so you have 20 times with 2. So means that this is the dimension. So if you want to build a maximum box, the box with maximum volume with the size given 9 cm and 9 cm and 24 cm length, so you have to build the box such that the height is 2 cm, right? It's 2 cm. So you have to cut out 2 cm, a square, the size of 2 cm from each corner so that you can form a maximum volume. So then what is the maximum volume? So the maximum volume here will be, you multiply all this, right? The maximum volume will be equals to 5 times 2, 1000, right? 5 times 20 times 2, you have 200, right? 5 times 20 times 2, okay, you have 200 centimeter cube. Alright, I think that's all for this problem. Hope you understand.